Let's record. So this is PSOC Creator 4.4. I have my 043 kit, which let me see myself here, which was a really neat idea to use a battery pack that Patrick had to run things. But this particular example, I want to show how we can read data in and off from a microcontroller. And I had a friend at, they make the chip for the Arduino. And now I've totally spaced their name. And he said knowing how to do the GPIO, general purpose input output, was one of the main things you had to know for microcontroller design. Atmel. I guess too much vacation for me. Atmel makes the chip for the Arduino IDE and kits. So anyway, let's create a new project. The target is the 043 kit, Sci8 C kit 043. And we're going to use an example. And you should be able to see, and I know you're not following along, I'm going too fast, but I am recording, so you'll be able to figure everything out. So you have the A to C SAR, so analog to digital converter, successive approximation register, sequential, and you reading the die temperature. Oops, and I need to select it. All right, and just like everything, all right, you have kind of the data sheet. Here's the pins, but this works, by default. Tells you everything that's going on, which now is as good as time as any. Is that there's a module that measures the temperature of the IC, and that comes into analog to digital converter, and there's a MUX, which is selecting that. There's our 12-bit successive approximation register ADC. Then there's a timing subsystem that we don't really have to look at. And then here, we're transmitting through the UART. Universal asynchronous register transfer. That's my first guess. And this is all the setup, but really to get where we want to go, we just have to. Okay. So now, yeah, certain things we can just look at, and let's see what for configuration. Not much for the die temp, because it's just reading a volt. There's basically a thermometer on the chip. Here's our ADC, and you can set how many samples you're taking. There's a V reference select, 1.024 volts, and that reference basically is telling you how narrow or how small a voltage you can discretize, right? Average things 256 times before you read it out. Then there's a resolution, there's an averaging mode. There's it's almost like there could be a class, two classes just on using that, okay? But it's all set up nicely. The timing subsystem I don't want to go into. And here, the UART, It's just very simple. The baud rate is 115,200, and the pin assignment is static, and that's all fine. Let's look at the C code, which, yeah, you know, with an op amp, you wire up the capacitors, the inductors, the resistors, and whatever. And to me, it's so much easier than, you know, you start writing all this code, right? I found that's okay. When you run it, then it becomes available, right? But you guys all have had, I think, 120 or definitely some C class, right? And they're, you know, what is the channel, ADC channel temp, injection period, what is the die temp, VREF, you know, all these various things. And then here's where it's printing it to the UART buffer. So that function, it's already defined for you, and you're just putting that in there. All right. Then it's going to do some calculation, right? Into 16-bit integer. That's a 32-bit integer. And so here's, so what is the temperature? It's got this convert the die temp into Celsius, right? Because it's just coming off of a voltage. So the Celsius is going to take the input from the A to C and convert it to an actual number. And then it's going, this is what's going to be sent to the serial port. All right. So let's program and the first time takes a while. What I'm going to do in the meantime is you can read things off with secure shell, and there's one called putty. And you just download it and install it. Not a big deal. So we'll just leave that there for a second while this is going. Oh, still going. That first program, or first compile, it's pretty extensive. Oh, and there we go. It's successfully done. If you're looking at the board, the amber and the green LEDs are on. All right. Then what we want to do in putty is connect to it, but a serial, but you have to put in the right baud rate, bit per second, and you have to put in the right line, and you might not know which one it is. So there is, I have to find it, bootloader host. All right, so if you go to tools, bootloader host, right, there's the UART, that's the one we want, is on COM4. And it looks like I have some Bluetooth on this computer, COM5, COM6. And this kit is IC squared, which is just another standard, okay? And, you know, just a note on standards, right? USB is a standard, right? And it will tell you how fast it, you know, there's various ones, what do the pins look like, the connections, so that anybody who does USB, it doesn't matter, it'll all connect. So even this battery brick that I got from an educational conference has USB. I don't have to think about it. That standard's already set. Another one is RS-232. All right, so it's for serial connections, and it same thing. They'll tell you all how the pins work. Now the thing is that a lot of times the RS-232 is configured now into the USB, so it's rare to find an RS-232 connection like this. People, universal serial bus and RS for the serial, right? Recommended standard. Oh, I guess I'm wrong. Recommended standard. But anyway, it's a serial standard nonetheless. All right, it's all there. So we found that it's COM4. And I just need to so even though it said it was 90, the bootloader said 9600 baud, this is really the baud rate when you've done it. So so now I should be able to connect to COM4. And here we go. So it's reading a channel 1 and channel 2, and those are just in millivolts, right? And then it prints out the temperature in Celsius. Right. So I mean, and so in some ways, something like this can totally ruin science fiction for you. That if, you know, Star Trek, they meet an alien and somehow they can communicate perfectly. Let's not even get into speaking. Everybody speaks English, but you know, all this universal standards makes it so that, you know, we can communicate with our own devices, right? Let alone alien races. Yeah, using putty and usable Jesus. Yeah, so it's still awesome. Don't get me wrong. Now, I just wanted to take it. Of course, I got to take it one step further. So I'm gonna get rid of that. I'm gonna kill it. Of course, you know, I want everything in Python. And so, you know, I just Googled, you know, communicating with USB or serial communication Python, right? Just don't even have to spell it right. So PySerial is a package. It doesn't come installed, right? But it tells you know, how to configure ports. And somewhere there's usually a little bit of sample code. And usually if you type in something like Stack Overflow, they've always got an example that I can modify. I never have to write like code from scratch. Although this looks like a different example. All right. But the code I got was definitely from one of these sites. So we did, for this particular, I was trying to, of course, I wanted a plot, but really you just need this module serial. But in order to install it, right, Pi serial. You just go to PyPy and pip is the installation, install PySerial, that copies it. And then I assume you're all using the same, so you go to the Anaconda prompt and just paste that in there. I've already installed it, so requirement already satisfied. So this is probably the first thing I've ever done with you guys where you had to install an additional package. Another something, there is this set of tools for linear circuit analysis. I wonder what's with. Is this all from you, Alex? Anaconda takes up way too much space. Hey, Alex, can we just talk about that a second? Because I don't think I understand the question.
Yeah, I've often just, when I program or anything, I install Python and like virtual environments and all that. But some class, maybe it was yours, we had to install Anaconda and it was like 10 or 13 gigabytes. And I just didn't understand what the value was, because when I went through the class, I think it was basically the same thing I do with Python and virtual environments.
Yeah, probably the trade-off was in a very short amount of instructions, everybody can come to the same baseline.
Okay.
Without me having to do that, and not, and figuring if somebody's already an expert, they'll just ignore me and they'll get, it won't matter.
Okay, that's good to know. I just, it seemed like a lot, and maybe other use cases or standardization, but that's good to know, so I don't have to keep it.
Okay, so just as another thing, right? There is this Python circuit analysis tool where you don't draw the circuit, you actually program, the connections, but you can, so just to show you, so you define H as a transfer function, right? And then you just type in H of T and it does the inverse Laplace for you, things like that. And that's another package. It doesn't come with the tool, with the Anaconda distribution. But it's pretty cool, but I still haven't kind of implemented it in 110. I guess there's enough going on in 110. So anyway, back to this. So there, you define the serial port, right? There's my COM4, there's that byte size, timeout, stop bits. You come up with a serial string, you just predefine it, I guess, as a string. I can't see the. Oh, okay, because that's all. All right, the reason why I don't see any more is because that was it. So you have a serial string and then it's an infinite loop. So while everything is true and nothing makes it untrue, serial port, and you just read the line, and you just press play, and now it's in Python. All right, now this is pretty simple, right? Notice when I just killed the hyperterminal or the PuTTY, right, I was still able to now use Python without anything going wrong. So now if I stop, right, and restart, I'm getting an error because I didn't really let go of the resource. So I just unplug it and plug it back in. Because I'm not sharing the sound, you don't hear that little. And so now we're getting it again. I was trying to come up with an example where I read some data and then plotted it. And then even had kind of like an oscilloscope like animation, and it worked. I don't know. I didn't think it was really ready enough for prime time. But so this, like my approach, let's just stop this. All right, let's see. So let's say I'm doing something else. Okay. I'm just looking for the, so I want to read random numbers. So int, oops, 16 rand. And yep, I found that going between Python and C is tough because Python doesn't have this semicolon to deal with. Temperature equals random number times 100 plus 1. And I'll just comment this out. Oh, I already did it. I said I was gonna, I already forgot the semicolon. All right. And I'll just press that again. And it's just complaining that I didn't use something, but it should work. Okay, says it's programmed. Oops, forgot to. So it would be better in Python to have some, if there's an error or if there's an interrupt or the program is stopped, that it'll automatically let the resource go. So there's my random number. Not quite doing what I thought it should do, but so the thing is what, let's say, like I have this example, but what I want to do is read the data out. Let's say we're doing, oh, I don't know, a stochastic resonator, right? Which you could program in C, right? But I want to read the data out, and maybe I don't have an oscilloscope, or maybe I do, but I'd rather plot it in Python, right? I can read the data off that chip, but I start with something that's working, right? And modify it like one line at a time. That tends to be my way. But you guys had 120. Maybe all this is like easy for you, except for Alex, where it was easy for her before 120.
Okay. Thanks. That's, yes, gotta laugh. But I think the way of like editing, modifying line by line works pretty well. There are just some products, like one of them I got into last semester, where it was just so convoluted. that they had like, it was Bluetooth, to be fair, so there was a lot going on, but I can't think of any other way you can make it work. Writing it from scratch is just too much work.
Right. Oh, that's good to have that confirmed, because that's what like with the TCAT, I think I showed a few weeks back. It comes with like almost the same amount of code, maybe even more for some things. And usually it's not like a syntax error. It's just, it doesn't, it just does wild things. So you end up modifying one thing at a time. Now, I guess the next one I want to see that's pretty cool is, let's see, file, new, project, target, code. I'm looking for, cap sense, proximity design. And this is, so you have, it has a cap sense module. Oops. Where you actually have a wire. This is off chip. If blue, remember, is like off chip. So you just connect a wire to the thing, and using our 140 knowledge, we alter the electromagnetic field or the capacitance. It's as measured by changing the capacitance, which then, let's just see the configuration. All right. So interesting enough, right? Any sensor needs some kind of filter, right? And you can see all the various filters there. So you could, I mean, this is all just to do capacitive sensing, which you can actually make a capacitance, a thing change with capacitance very easily, but to get it like to really work on a smartphone is actually quite difficult. And then depending on how close you are, the pulse width modulation will blink this LED, faster or a higher duty cycle or less duty cycle. So let's see if it'll just program it. So Alex just put something in the chat. Maybe, I can always make these chats available, but maybe you want to grab that information before the end of the session. All right. Now this is something. Okay, so I was running into this. Here, I'll just. Where are you guys? Let's see the screen. So when you're running it, you just put in a wire like this, and then when your finger comes close, this blue LED gets darker. No, yeah, darker the closer you get, and brighter the farther away you get. But what I found is that when you're switching projects, it doesn't always program. And I thought I'd found a solution, which there's something like unload.
Unload reload project.
Yeah, it's just I want to. And remove that from the workspace.
What's that little button you just pressed? Like if you.
Yeah, I don't know. I'm just using the force here.
Okay. Well, in these
No,
programs, it takes the force to get it working.
I mean, what it is every once in a while this pop-up comes up, like it doesn't know what, like it's forgotten what kit it's going to, or so which port is it going for? Oh, now I know. All right, no, now I remember what happened. It is working. It's just on the all right, this guy. All right. He changes the pins. And so that's got to be P06. But the pin LED, I'm just going to randomly, like it's smart enough that if you're already using a pin, it won't let you use a pin. So P06 was being used by the LED. And then what does he use for the LED? P16 for the LED. Port 16. Okay, I forgot about that. So so I just clicking fully program everything, which is probably the most inefficient way to do it. But so it comes here, there's port settings, internal there, that's just the power. So I do port acquire and just click on the kit in question. And then it seems like it's fine. So although it's, oh, okay.
And what were you using for the proximity sensor? Or where
A
is that on?
wire, a wire. I'll show you in a second.
Okay.
As soon as hopefully it works. Which when I can't screen share it. I'll have to put it to a battery pack and then you'll see it.
Okay, gotcha.
But this the guy's video is pretty good. He goes right through, tells you, it worked, following his example and what to do. It worked right off the bat. Oh, okay. So let me. All right, just give me a second. I'm sorry. Okay, so I'm gonna have to. Let's see, where's Zoom? I'm gonna just stop share so I can see what I'm doing. Okay. So that blinking like that, I'm just gonna, can I pin myself? Okay. So you can see it blinking. That means it's kind of not sensing anything, right? But now if I bring my finger closer.
Whoa. That's pretty awesome.
Okay. And then if you kind of leave it for some time, it'll just go there. So yeah, I'm still kind of geeking out about that.
That's pretty
So
clever.
of course I wanted to now read the data rather than do the LED. I wanted to read it off of the serial bus. And I think, well, I got a bit stuck. Although I think I'll just, okay. I'm just going to bring it up in putty. Oops. Come forward. Not quite sure what happened, but it stopped. All right. Okay. Let me. Okay. So now it's plugged into my computer. interestingly, if you put in the wrong baud, you tend to get garbage. And I think maybe it's just, it's not set up. Like it's not converting it to maybe a format that I can read, but so that jumping around on the screen is me putting my finger closer and near the wire. So I'm affecting the computer, right? It's just not reading it in any way that you can figure out. And if we, that's the pins, TMA. Where's that? So in this case, it's got the a different, maybe it's a software debug TRX. But it's not the same. It's not configured as the same way as the ADC one was. The ADC one, and it was sending integers. I'm not quite sure what it's sending. So I hadn't figured it out yet, but that's as far as I got, but it's still pretty cool. But you know, the thing is right, just when, let's just say you're using a regular C program and you're trying to figure out what's going on, right? You put in interrupts, or you have various print statements to verify that what you just calculated, you know, was actually what you meant it to do. But of course, you know, if it's running on the CPU on a board off the computer, you need to be able to see what things are, right? And so this is a great way to get data off of something in a serial fashion. It just, and so actually I was going to try to start from scratch, quotation marks, scratch, with just write a program, it generates a random number and it sends it out on the UART and you just read it and plot it. And that to put in the bare minimum. Although probably what I'll end up doing is I'll keep deleting things from the A to D, the dye temperature example, until I'm only left with a UART and some kind of random number generator, you know. Anyway, that's pretty much all I have.
Cool. That's a neat demo of the board. I know we had the meeting with Patrick Kane, but it felt maybe a little more markety. So it's nice to see the board in action. I'm still not sure I really understand, like, it sounds like it's nifty because it's a PSOC or it's programmable or what have you. And like, I'm hearing when people explain what that is, I'm hearing that. But as for like really understanding it, you know, viscerally, these examples also just seem to mirror my other experience with like microcontrollers and stuff.
Yeah, I think, oh, well, that's,
Like a use case where this is handy and regular, you know, regular system on a chip or something like that is just limited. But maybe I should just Google it, you know.
no. So like, here's you know, a TI kit, right? the MSP 430. So it was another, MSP 430G examples. Okay. So here's another one that they use in EE30, or no, they updated it. It's,
are you meaning to
oh, am
share
I
your screen?
sharing? Oh,
No.
I am meaning, and I'm not. Okay, so this is the MSP 430.
Yeah.
We're using a different one now, but it's the one they gave me for free, and I just kind of,
Yeah, we're using the
I'm just
430.
trying to think, yeah, like, so this is a kit, right? Which hopefully, it's been a while since I've read through, but let's see what it has, right? So it's got 16-bit RISC architecture, low power modes, 12-bit A to Ds, and comparators. (16-bit timers). So this here, CRC, actually they have that too in the PSOC. I don't know how many bits. Now, this is something interesting. It's got a 32-bit hardware multiplier. I haven't really seen that on PSOC. Okay. I know what a Manchester carry chain is. Codec, I don't know. I'd have to look it up. But it's got the, you know, they all have this kind of thing. On shift. Okay. So these are the you know, these are, now this is like one of their, I call their low end microcontrollers, right? I think what the PSOC, so the environment is totally different, right? I've used the TI environment and it's all just C code. And in fact, that one of those neural models, the quadratic integrate and fire, I actually programmed into the TI chip, but I wanted to get the data out. And I guess I didn't know how to use a UART. So I thought, well, they have a pulse width modulated filter, a pulse width modulated signal coming out. I'll create a filter, which then led to a whole host of issues, which now is why we covered in 110 or 110 lab, right? So here the PSOC, you know, it has this kind of graphical interface, things pre-done modules that you can just kind of configure however you want, right? Where it's all done in programming. At least that's what I remember, right? And they have like, it's almost like schematic capture. Oh, I want an A to D here. I'll put that A to D there. Oh, it has OPAMPS on it. Oh God, how did I forget? So I forget how many, but it already has OPAMPS on it, right? So the thing is for, let's look up one of my favorite parts, LTC 1630.
I guess my general understanding, like, it kind of sounded like it was just another term for like a system on a chip, except there were some components we were talking about changing analog
Yeah,
parts.
I get what it is. Is it so? Let's go through what I know. So we have anadigm, which has essentially almost everything is analog. And it's all based off of switch capacitors, right? So I have a built-in filter and I want to, what do I want to do? I just say, what's the corner frequency? And it programs the switch capacitor to make that filter happen, right? I've got resettable integrators. So that's all like an op amp with a reset. It's got a multiplier, right? And so pretty much everything is analog, but there's like a whole list of, there is another, they have their own ADD, right? And I believe they have some C programming ability, but I hadn't wanted it for that, so I didn't really explore that. But so this one is like almost exclusively analog. The let's say that one TI chip I looked at, even though it had maybe analog functions, it's all digital. It's all these pre-done blocks that are connected to a microprocessor. And the PSOC has actual op amps on it. So it's kind of a cross, right? It actually has op amps. And some of the newer PSOCs, it has analog filters that were just like, I'm clicking on this, cam settings, right? What's the gain? What's the cutoff frequency? It has that same functionality, just not on our kit. So you could call it in between, right? This is like in a way a good senior project type question is let's say we have something we want to build. Well, most people will go with what they already know. So let's say you've been using Arduino. It's very hard for people to switch a complete integrated design environment, right? To go with another chip. And so, so most likely you've seen the TI environment in 120, right? Maybe if you've had 138, I think they have the Atmel design environment, but they kind of stopped making it. And so I think they went to TI. But you said, well, I want an Atmel microcontroller. I want to evaluate TI microcontrollers. I want to evaluate Cypress PSOC, which, yeah, it's a clever marketing term, right? And I did like his thing about where it's used and who the customers are, because before I embark on something, I want to make sure that students are going to need this in industry before I devote any time to it, right? And trying to get marketing information out of the anodyne was kind of hard. Like, well, who are your customers? It's a secret. Well, I use it because it's pretty neat for my research area, but so you have a target thing. Well, how do you evaluate which microcontroller is the way to go when you might have to know 3 different integrated design environments, right? Where, yeah, if you already know TI, well, they have probably 30 versions of the MSP 430, which you can then choose with various things. Just like picking an op amp, right? Just picking parts is actually one of the hardest things. a student's working on a switch, a power supply, right? Except it's not just a small one. It's minus 48 volts at maybe 10 amps or something. And if you look at the circuit, it's a transistor, inductor, diode, capacitor, resistor. And an input is an input of a square wave. And picking that transistor has proven really difficult because I've never done that. I've always dealt with data where the powers are small, right? So it turns out a lot of these transistors are so big that there's a lot of current flow through the gate. Although we all learn, right, there's, you know, gates are ideal capacitors and there shouldn't be any DC current flow. But when they're really that big, and even there's AC current flow, selecting a transistor that can actually move that amount, switch that amount of current, but can be driven by a 555 timer, it's actually it's not trivial, right? So picking parts is really difficult. And you might have heard me mention before that, yeah, even, you know, once you get an op amp with the right gain bandwidth and the offset voltage and all of that, will they even make it for you later, right? If you're committing to an op amp with a certain characteristic and certain pin out, and then the company upgrades on you, right, and changes the pins or does something, you know, it's very scary sometimes. So, but yeah, probably. So in some ways to say, what is the difference of PSOC would probably be a bigger marketing conversation if they could actually say what can be done, right? And this is actually like the simple one. PSOC in general. But of course, the other ones have. You know, all right, maybe I've spoken too much.
No, that's I think there's a lot of good information. I guess like my thinking was that this has, you know, a mix of digital and analog, and that's great. But all the examples we tend to go through, kind of like you said, you know, they each have their own, you know, converters. They get things done in a different way. So it was like, what's an example of an area where a PSOC, which has analog and digital components, excels, where one of these other devices doesn't? And it kind of sounds like the answer is, well, probably one, keep going into your senior project. But the other thing being, well, analog versus digital. So if you have a use case where you're really trying to hone in on something that's analog and you just have a digital microcontroller, then maybe you're interested in a PSOC.
So like, here's the thing, you know, as you know, right, my applications tend to be education, right? Just trying to find out how much something costs. Okay. Sample and buy. Buy. That's the key. So for the PDIP, and if I'm buying 1,000, right, it's 340 a piece. Okay. I think PDIP is through hole. Yeah, it's through hole. Okay. So now let's say I'm trying to outfit a student lab or something, right? So this PSOC kit, right? And I think it has 2 op amps built into it, right? Is $10. So yeah, it could be, yeah, it's like just to even if I only use the op amps, I'm almost ahead of the game, right? And leave it at that, right? But it's interesting too, the phrase analog versus digital, when really it's analog and digital, and choosing, like anything in the real world has to have some analog component, and deciding where you're going to do the processing, right? So usually an A to D needs some kind of filter before it. So what I could see is, why would you want an op amp on the chip? Is that some sensors, right, really need more processing and filtering and level shifting before it gets to the A to D. So like pressure sensors, right? Which, yeah, you can probably buy almost any sensor on its own little board, right? Where it's already got a filter on it, and you can just connect it, digitally, right? You can, almost every sensor comes that way. But if maybe you don't want that little board, and now you want to kind of integrate it all onto your own thing, right? So pressure sensors, I think they run off of like a 10-volt power supply, and then you not only have to filter it, but you also have to amplify it and even adjust the level, which can be done pretty easily with an op amp. Now, if that op amp is already on the chip, right, you just have to supply some surface mount resistors, and you can go for right there, right?
I think those are pretty good examples. I mean, just when you were comparing the price of op amps, like I'm thinking, well, as students, we got to keep our resistors and capacitors and stuff, but none of the op amps. So technically, if nothing else,
Yeah.
I have 2 op amps. And then your example with filtering kind of hits home, because when I was doing like a heart signal, it was using an eval board, and it filters that, makes it all nice and pretty. And then I was feeding it into a system on a chip, but of course I'm not going to put the eval board in whatever I'm going to create, or at least not in this case. So
Right.
there's going to have to be op amps in there.
Yeah, you kind of, so you actually bring up an interesting thing, is that you probably know there's a company called Adafruit, where they've taken just about anything you could want and put it on a board and made it so that you can, connect it digitally to just about anything you want. And so, and that's great, right? But if you then are trying to integrate it, well, you can't really use it, right? Be, and some might say, well, they've done all the engineering, they've done all the electrical engineering for you. What's your part? You just connected a bunch of parts you bought. However, when you're trying to program your system, right, you don't want to wait for this board before you can start programming. So you can use all these Adafruit components, hook it all up, right, and then get your own code working, right, for the system. And then when your board comes back where you've done the engineering yourself, right, you know that the code is rock solid, and anything not working is probably some kind of interface issue. So it has a role, right? It's just, yeah, if computer engineers, yeah, they're probably fine with buying all these pre-done boards because they're not, they don't really get into the physical part, EE 140, for example, right? Or, a chip heating up on you. And two, the biomedical engineers, they've kind of gotten away from, like, let's say EE 98, and they just kind of want to know what it's like to hook up an EKG. They don't need to make the circuit to learn about an EKG system at a system level, right? So yeah, hooking up boards like that is fine. I don't know.
Cool. Thank
Well, this
you.
is
That helps.
and this is a 32-bit. And yeah, not only that, but I mean, this thing can be turned, this particular thing can be turned into a mini oscilloscope, which other ones can too. They just, I just want to get a picture of the parts they used. So we have a voltage coming from the DAC, and then here's the op-amp buffer, 2 resistors off chip, and well, there's a reason for the op-amp right there. So the DAC needs a buffering. That's the negative and the positive. I don't know what that is about. Oh, it even has its own function generator. Now, yeah, their example, you can get an LCD screen to plug in, right? But if you've got the data, right, well, put it into the UART and send it to your computer, right? And I almost went for this in 110 lab rather than the other one, but the M2K from Analog Devices was so turnkey, and had so many other applications. I went for that. But no, yeah, I don't know if these issues are the fact that it's just not a great oscilloscope, or the function generator isn't that great. But anyway, so, and yeah, how does that feed into us is that we can look at these stochastic resonators rather than making them with the Schmidt trigger, which, is totally possible, right? We can actually program the actual equation using fixed point arithmetic, right? And, do it all in the PSOC kit. Now, yeah, the Bluetooth for this kit, you got to buy a chip and solder it on yourself. Okay. I finally figured that out, because when you go to add parts, there's no BLE there. So finally figured that out. And yeah, and this is something that's kind of neat for me. I try to be agnostic to parts or companies because we have so many. But it is so, I'll just say, the reason why I got into the TI microcontrollers is somebody gave me a free $10 kit, and how many hours I put in on that kit for $10. and it's actually in our curriculum because of the pulse width modulated DAC filter, right? All for $10. And it's just, I don't know, I guess I'm just really cheap. And so to have these donated by Patrick, yeah, got me back into it again. Yeah. I mean, the M2K at $150 is, wow, that's pretty good. Now, yeah, there's a former student, they sent me another kind of integrated, it's like an oscilloscope thing that runs off of the PC, and it has better specifications, but it's like $400, $500, right? Where if you needed that, oh, okay, need it, but God, no. Moku. So it's an oscilloscope voltmeter, and it's got its own software. Let's see. Anyway, so these are a lot bigger. It's probably 3 M2Ks, but they're more than just voltmeters. It's like an M2K. It's got voltage sources, everything. It's just, oh, I think it can source and sync a lot more current, if I recall. And it wasn't available when the pandemic started, and the price point, we couldn't have done what we did. But it's something. I have one, so maybe we could use it. Anyway, that's again, I guess I say it again. That was really all I had planned. Well, that I didn't have planned. Those were great questions.
Awesome. Thank you.
Yeah. All right. So I'll throw this on the recording, so if you can follow along. But really, right on the PSOC 43 kit website, that guy's video is right there with the proximity sensor, and that's where I learned it. Okay. All right. Have a wonderful day. All right. Bye, guys.
I have a kind of personal question.
Oh, hold on. Then let me stop recording.
All right.